Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we understood how to verify causality and stability of a linear time invariant system in the Z domain. In today's video lecture, we'll analyze linear time invariant systems using Z transform. Let us consider a linear time invariant system characterized by its impulse response h of n, and let input to the LTI system be x of n and output be y of n. We know that output of a linear time invariant system for any arbitrary input can be taken as a convolution between input and the impulse response of the linear time invariant system. Therefore, output y of n can be obtained as convolution between the input x of n and the impulse response h of n, represented by x of n asterisk h of n. The output will be convolution between the input and the impulse response, or impulse response is also referred to as unit sample response. So y of n in terms of convolution summation can be written as summation k minus infinity to plus infinity x of k h of n minus k. And also we know that the Z transforms of input, output and the impulse response can be denoted as Z transform of input signal x of n can be denoted as x of z. Y of z will be the Z transform of the output y of n, and h of z will be the Z transform of the impulse response h of n, and h of z is also called as system function or transfer function of linear time invariant system. Now, according to the convolution property we studied in the Z transform, first equation represents the convolution between two time domain sequences, one input and another one is the impulse response. So according to convolution property, equation 1 can be represented as y of z equals to Z transform of the convolution between input and the impulse response. According to convolution property, if we are performing convolution in the time domain, then its equivalent operation in the frequency domain will be multiplication. So y of z will be equals to multiplication between Z transform of the input and Z transform of the impulse response. So it will be represented as x of z multiplied by h of z. Rearranging the terms for h of z will be written as the ratio of the Z transform of output to the Z transform of the input, y of z divided by x of z. Here h of z is called as the transfer function or system function, and Z transform of the unit sample response h of n. Therefore, in the Z domain, system is characterized by a system function or the transfer function. And we know that any discrete linear time invariant system can be described by a linear constant coefficient difference equation, and the general form of difference equation is given by summation k equals to 0 to n ak y of n minus k equals to summation k equals to 0 to m bk x of n minus k. Y of n minus k are present input and passed out. Y of n minus k are the terms containing present output and previous outputs. X of n minus k contain present input and past inputs. AK are the coefficients associated with the output terms and BK are the coefficients associated with the input terms. Now rewriting the above equation to obtain the output y of n, the expression will be y of n equals to minus summation k equals to 1 to n ak y of n minus k plus summation k equals to 0 to m bk x of n minus k. Separating the first iteration from the summation on the left hand side, we'll be able to write the difference equation to get the output y of n. Now taking the z transform of this output y of n, we can represent it in the z domain as z transform of y of n will be y of z minus summation k equals to 1 to n constants ak will be represented as it is, and z transform of y of n minus k, y of n minus k is delayed output terms. So according to the property, y of n minus k z transform will be z to the power minus k y of z plus summation k equals to 0 to m bk will be written as it is, and x of n minus k z transform will be z to the power minus k x of z. Now rearranging the terms, y of z can be taken common, and taking the ratio y of z divided by x of z will be written as summation k equals to 0 to m bk z to the power minus k divided by 1 plus summation k equals to 1 to n ak z to the power minus k, which can also be written as h of z, which represents the transfer function or the system function as an ratio of the z transform of output to the z transform of the input. This transfer function is expressed as ratio of two polynomials, a numerator polynomial of different powers of z and the denominator polynomial of a different powers of z. Therefore, z transform reduces the convolution operation into simple multiplication. To obtain the output of linear time invariant system, instead of performing convolution between input and the impulse response, we'll apply z transform and obtain z transform of the input and impulse response. We'll multiply them together. We'll multiply x of z with h of z. Z transform of the input and z transform of the impulse response will be multiplied together, and on this product we'll take inverse z transform, which will give us y of n. The output y of n will be representing the output of linear time invariant system in the time domain, but this time y of n will be applied as an inverse z transform of the product of the z transform of input and the z transform of the impulse response. So we'll be able to obtain the output of LTI system by using z transform, and the advantage of using z transform to obtain the output is complex convolution operation will be reduced to simple multiplication operation. We'll consider a problem. Compute the response of the system described by the difference equation y of n equals to 0.7 y of n minus 1 minus 0.12 y of n minus 2 plus x of n minus 1 plus x of n minus 2. To the input x of n equals to n into u of n. Now, is this system stable? A discrete time system is described by a difference equation where y of n is the output, y of n minus 1 is 1 unit previous output, and y of n minus 2 is 2 units delayed output. X of n minus 1 is delayed input and x of n minus 2 is 2 units delayed input. And the nature of the input for this linear time invariant system is a ramp sequence, because x of n is defined as n into u of n. Now we'll write the given difference equation and we'll apply z transform. Z transform to take the z transform of each term in the difference equation. So z transform of the difference equation will be y of z equals to 0.7. Z transform of y of n minus 1 will be z inverse y of z minus 0.12. Z transform of y of n minus 2 will be z to the power minus 2 y of z plus z transform of x of n minus 1 will be z inverse x of z plus z to the power minus 2 x of z will be the z transform of x of n minus 2. Now combining the input terms and the output terms, we can take y of z and x of z common, and rearranging the terms as the ratio, h of z can be represented as y of z divided by x of z, which will be equals to z to the power minus 1 plus z to the power minus 2 divided by 1 minus 0.7 z inverse plus 0.12 z to the power minus 2. Now this is the representation of z transform of the or transfer function as a ratio of two polynomials. Now rewriting this ratio for the positive powers of z, will get z plus 1 in the numerator divided by z square minus 0.7 z plus 0.12 in the denominator. And denominator polynomial is also referred to as characteristic equation, and roots of the characteristic equation will be poles. Therefore, h of z can be expressed in factored form as h of z equals to z plus 1 divided by z minus 0.4 and z minus 0.3. 0.4 and 0.3 are the two roots or two poles. Now as both the poles, they'll be inside the unit circle, hence the system is stable system. Both of the poles or the pole values are 0.3 and 0.4, which are obviously less than 1. So both these poles will be inside the unit circle. And according to the stability condition we studied in the previous class, all the poles of the stable linear time invariant system should be inside the unit circle. Here they are inside the unit circle. Therefore, the system described by the given difference equation is a stable linear time invariant system. Now the input is given as x of n equals to n u of n, which is a ramp sequence. Taking the z transform, or we know that the z transform of the ramp function will be x of z equals to z inverse divided by 1 minus z inverse whole square, or writing this for the positive powers of z will give us z divided by z minus 1 whole square. Now to obtain y of z, we'll multiply x of z with h of z. Multiplying x of z with h of z will give us y of z equals to z plus 1 divided by z minus 0.4 multiplied by z minus 0.3 multiplied by x of z, which is z divided by z minus 1 whole square. Output y of n can be obtained by taking inverse z transform of y of z. So to take the inverse z transform, we can use any of the three methods we studied in the previous class. Either we can apply power series expansion method, or we can apply partial fraction expansion method, or contour integration method. Most of the times the output, z transform of the output, in most of the cases the z transform of the output y of z will be expressed in the rational form. So generally we'll be using partial fraction method out of the three to obtain the inverse z transform of y of z. So to apply the partial fraction expansion method to obtain the inverse z transform, we'll rearrange y of z to y of z divided by z by sending one of the term in the numerator on the right hand side to the denominator on the left hand side. So we'll express y of z divided by z equals to z plus 1 divided by z minus 0.4 multiplied by z minus 0.3 multiplied by z minus 1 whole square. So we'll be having four residuals a, b, c, d, each assigned to one of the pole, and we have a repeated pole at 1. So we'll apply partial fraction expansion method and obtain all the four residuals. A will be equals to 38.89, B will be equals to minus 26.53, and C, which is for a repeated root or repeated pole, will be equals to minus 12.35, and D, after for a repeated root, will get its value as 4.05. 7, 6. We'll use this to represent y of z divided by z. Y of z divided by z will be equals to 38.39 divided by z minus 0.4 minus 26.53 divided by z minus 0.3 minus 12.35 divided by z minus 1 plus 4.76 divided by z minus 1 whole square. Or writing this in inverse negative powers of z or inverse z transform form, y of z will be equals to 38.39 divided by 1 minus 0.4 z inverse minus 26.53 divided by 1 minus 0.3 z inverse minus 12.35 divided by 1 minus z inverse plus 4.76 divided by 1 minus z inverse whole square. The first term will be 38.89, the residue, multiplied by the term in the denominator, which is 0.4 to the power n multiplied by u of n. Likewise, we'll write the time domain equivalent of each term in y of z. So it will be 38.89, 0.4 to the power n u of n minus 26.53, 0.3 to the power n u of n minus 12.35, 1 to the power n u of n plus 4.76 n times 1 to the power n u of n. Taking u of n common, the output for the given difference equation or for the LTI system described by the given difference equation, for the output, for the input x of n equals to n u of n will be y of n equals to 38.89, 0.4 to the power n minus 26.53, 0.3 to the power n minus 12.35 plus 4.76 multiplied by n of u of n. I hope all of you understood the concepts that we covered today. In the next video lecture, we'll be solving some more problems on the transform analysis of linear time invariant systems. Thank you all.